Okay, so after talking for a while about the two major types of bonds that we deal with, ionic and covalent bonds, we want to really dive deep for a few days into covalent bonds. So more particularly, we want to discuss the types of molecules that covalent bonds form. So if we take something like carbon dioxide, for example, CO2. So that is the chemical formula for carbon dioxide. So this tells me that in the molecule CO2 there is one carbon and two oxygens. But that's really all I know from the chemical formula. So the next step in exploring a molecule like CO2 would be to draw the Lewis structure of CO2. So a Lewis structure is simply a diagram that shows the actual layout of a covalently held together molecule. So Lewis structure is named after Gilbert Lewis. He was a famous chemist. He got nominated for the Nobel Prize over 40 times, but never actually won the prize. But that's beside the point. So a Lewis structure might look something like this for CO2. We could have something like this. Just based on CO2, we don't know how the atoms in CO2 are bonded together. We can have this. Okay. We could even have something strange like this. Okay. But it turns out that when you go through the steps that we'll learn momentarily and draw the true Lewis structure for carbon dioxide, it looks something like this. Okay. So without knowing anything else, just seeing CO2, you probably wouldn't have immediately gone to this structure right here. And so what we're going to do is learn these steps for drawing Lewis structures, and then we'll apply them to some different examples and actually draw them out. So the steps are somewhat complicated, so we're going to go through the steps first and just talk through each of the steps, and then in another video we'll go back and try and apply them to some examples. So these may be kind of difficult at first, but hopefully the more you practice them, the easier they'll become. So just a couple of notes before we start going through the steps and rules for writing Lewis structures. So each one of these bonds, okay, contains two electrons. Okay. So what I drew right here is a double bond. So there are two bonds between carbon and oxygen here. So this carbon atom and this oxygen atom are sharing 4 electrons. Okay. So the dots that we put around the oxygens here are just valence electrons. So each dot represents an electron, and they are not being shared by carbon. So I think you likely already knew that. Just be aware of those. You can have a single bond, a double bond, or even a triple bond. Okay, you can have a quadruple bond for reasons that you can discuss in higher level classes. But for now, just know these are the only 3 options. And we know that a single bond would be sharing 2 electrons, a double bond shares 4 electrons, a triple bond would share 6 electrons. And we know that these are covalent bonds because they represent sharing. So we know that we don't show ionic bonds with a formal bond like that. So let's go to the notes and just kind of talk through some of the rules for drawing Lewis structures. So I believe they begin on page 3 in your notes. Okay? So it starts off by stating that states the octet rule. So it says that compounds form so that atoms, either by gaining, losing, or sharing electrons, have an octet in their s and p orbitals. Okay, and that is the s and p orbital of their highest energy level. So that's where that number 8 that you likely learned in middle school comes from. You know, atoms prefer to have 8 valence electrons most of the time. Okay, that's not a great rule because it doesn't always apply, but it applies a lot of the time, so we'll use it quite a bit. And we know this magic number 8 comes from a field S sublevel that holds 2 electrons and a field P sublevel that holds 6 electrons. So that's 8 total. So in covalent bonds, or covalent compounds, atoms attain this octet, which is what we call it when they have their 8 electrons, by sharing electrons. They don't actually gain or lose them. So there's a couple of comments listed below about the octet rule. So hydrogen and helium do not follow the octet rule, because hydrogen and helium on the first period of the periodic table only can hold 2 electrons in their outer energy level. So hydrogen and helium only need 2 electrons, okay, to be satisfied or to be happy, for lack of a better word. So the second row pretty much follows the octet rule. The atoms that we come in contact with most often, the carbon, nitrogen, oxygen, fluorine, we can assume they obey the octet rule. Notice I did not mention the metals on the first row. I did not mention lithium, beryllium. Typically, these metals will form ionic bonds. Okay, so if they form an ionic bond, electrons are transferred. Okay, so we don't need to worry about that. Beryllium we will discuss a little bit later. Beryllium actually does occasionally form covalent bonds. And then boron is an exception to the rule that we will discuss in just a second. So we already said that hydrogen defies the rule. It only needs 2 electrons. So boron and beryllium, they defy the rule. So beryllium, you can see having 4, 6, or 8 valence electrons. Boron can have 6 or 8. Typically, you will see boron with 6 electrons. Third row elements and heavier can exceed the octet rule because they can put electrons in their d orbital. Okay, so they can hold more than 8 in their outer energy level. So we look down, the noble gases defy the octet rule. Phosphorus, antimony, arsenic can have 8, 10, or 12 electrons. Sulfur, selenium, beryllium can have 8, 10, or 12 electrons. Chlorine, bromine, and iodine can have 8, 10, 12 electrons, and iodine can have up to 14 electrons. So it seems like I just told you more exceptions to the rule than there are atoms that actually follow the rule. And often that is the case. There are a lot of exceptions that we'll encounter. But if you want to go ahead and make a note on your paper, the most common exceptions that we encounter are boron, phosphorus, and sulfur. Okay, those are our by far most common exceptions to the octet rule. So when we start a problem, besides hydrogen and helium, we know they're always going to not follow the octet rule. They only need 2 electrons. But when we start a problem, except for hydrogen and helium, we're going to assume that all atoms follow the octet rule, and all atoms need 8 valence electrons. And then if we can't make a problem work out, and every atom have 8 valence electrons, then we'll start looking at what atoms might be exceptions. See if we have a sulfur present, a phosphorus present, a boron present, for example, and we'll go from there. So just to make sure we're on the same page about what's going on here, if you have these 2 fluorine atoms, it shows the orbital diagram for fluorine. So let's go ahead and review an orbital diagram, what that is. So the electron configuration for fluorine, you should remember, would be 1s2, 2s2, then 2p5. Okay, so let's just say I have 2 atoms of fluorine. So I'll go ahead and fill in these. So they each need 1 more electron to fill up their valence shell, or we could say to gain their octet. So their octet would be the 2s and 2p electrons here. So what we'll see happen is that the first fluorine atom can share this electron with this fluorine. The second fluorine atom can share this electron with the first one. So if they each share 1 electron with the other, they still maintain it, so they still retain it, so it still counts toward their 8, but it also counts towards the other atom's 8. So if they each share 1, now they have the full octet there, so now they have 8. So that would be a single covalent bond forming between them because they're sharing 2 electrons. Okay, so if you move down, there are a couple of notes about electron dot notation. You're likely familiar with these. Electron dots show the valence number of electrons. Don't forget that we find the number of valence electrons an element has from the periodic table. So if we go to the periodic table, group 1A would have 1 valence electron, 2A would have 2, 3A would have 3, 4A would have 4, 7A, the halogens, would have 7, 8A would have 8, except for helium. Okay, so helium's the exception there. Helium only has 2 valence electrons, only has 2 electrons total. So we can look at the A group number to determine the number of valence electrons an atom has before it starts bonding. Okay, so this stuff you likely already know, so keep those exceptions in mind. But now let's look down, let's look at the rules for drawing Lewis structures. So as we go through these rules, they probably won't make sense to you initially. They're hard to understand just reading them. This whole page of notes is difficult to understand the first go around. I just kind of want to talk our way through it. And then as we go back and do examples, we'll refer back to this page, and this page should make a lot more sense as we begin to move through and actually draw some Lewis structures. So these are the general steps for drawing a Lewis structure, sometimes called a Lewis dot structure. The first step is to determine the number of atoms and type of atoms in a molecule. So for that we look at the chemical formula. So something like CO2, we can say there's 1 carbon and 2 oxygens. So then we determine the total number of valence electrons to be used. So go back to the CO2 example. We could say carbon is in group 4A. So carbon would have 4 electrons. So carbon starts off with 4. Oxygen is in group 6A. So each oxygen starts off with 6 valence electrons. Okay, so 6 plus 6 plus 4 is 12, 16. Okay, so we know we have 16 valence electrons that we have to use up in this molecule. Okay, so now that we have that, we form a skeletal arrangement. So what a skeletal arrangement is something like this over here. So I drew these options where I had carbon, oxygen, 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 carbon, oxygen. Then I drew the little triangle. So these were our options for the skeletal arrangement. We typically want to avoid forming closed shapes unless the closed shape contains only carbon. Okay, so we typically want to stay away from something like that. So we had two options, carbon, oxygen, oxygen, or oxygen, carbon, oxygen. So symmetry is typically preferred. So this skeletal structure is more symmetric. So this is the one we go with. So that's our just basic arrangement of atoms. So in this arrangement, carbon is what we call the central atom. It's the one in the center of the molecule. So if a molecule just contains 2 atoms, there is no central atom, there is no center. But if it contains more than 2, there's usually a central atom, okay? So carbon is typically the central atom. Okay, so if we have carbon present in the molecule, carbon is going to be the central atom. If there is no carbon present, it is typically the least electronegative element except for hydrogen. Okay, so I'll say that again. The central atom is typically carbon, if that's an option. If not carbon, it is typically the least electronegative element. So we can go back to the Pauling electronegativity table and find the one that's least electronegative except for hydrogen. So hydrogen will never be our central atom. So in this case, just by attaching the atoms, I already used 2 electrons, 4 electrons. So I have 16 minus 4. So I only have 12 electrons left. So I have to put 12 electrons somewhere around this molecule in the form of dots. Okay. So once I place my electrons, and we'll talk about some strategies for placing them as we move forward. Once I place the electrons, I need to do 2 things. I go back and I double check that I use the correct number of electrons in some combination of bonds and lone pair electrons. So electrons that exist in pairs as dots that aren't bonds we call lone pair electrons. And we'll abbreviate that LPE often, so lone pair electrons. So make sure we use the correct total number, and then make sure every atom has 8 electrons around it, unless it's one of the exceptions like hydrogen or phosphorus or sulfur. So everything needs to have 8 electrons around it. So if it doesn't have 8, and it's not an exception, you know you've gone wrong somewhere. Okay, so our first option is just placing dots around it. If we can't make everything have a full octet, if we can't make everything have 8 electrons around it by only placing dots, that's when we go back and try using double bonds and triple bonds. Okay, so double bonds and triple bonds are kind of our last resort to make the Lewis structure make sense. So remember, if we place a double bond, that's 4 electrons instead of 2. And it's kind of a trial and error game. So you do trial and error until you get a structure that makes sense, that you can go back and count. Yes, I use the correct number of electrons, and yes, every atom has a satisfied octet, or it's one of the exceptions to the rule. And then once we get to our correct final answer, in this case, through kind of trial and error, this gives us a kind of crude picture of what's actually going on in the molecule. Okay, so this is how we visualize how the molecule of CO2 is held together. So I realize that was kind of a crash course, and you probably, after watching this video, won't be able to go and draw a Lewis structure on your own. You might be a little bit confused about that. That's perfectly okay. That's kind of the way it's intended. We go through the basic rules at first, just so you have a background idea of them. You have the basic idea of what we're trying to do. And then in the coming videos, we'll go through these together, and we'll go through the steps one at a time and draw more Lewis structures, or actually draw our first Lewis structure. And then as we do it, hopefully they'll make more and more sense, and the process will become much easier for you.